Okay, and backwards. Okay. Huh. Good afternoon, everyone. Nice to see you guys. First of all, thank you very much to taking the time to listen into the journey of autonomous machines and going through step by step how we in Parker will build the building blocks for the next generation of machines in the mobile market space. So before we're going into really in-depth what we will do, I just want to introduce myself. So my name is Nils Henriksson, coming out from a location in Sweden, in Borås, where we have a Motion Center of Excellence team, where we're putting all the Parker components together, and we can actually test it so we make sure it actually works as a system for our customers. I've been in the market for over 35 years, background in electronics, hydraulics, and lately the last 10 years in electromechanical for electrification on the mobile machinery. So the areas what I would like to talk about today, it's about autonomous machines, of course, but it's also about controls, the valves, and the impact on the electrification for our future machine controls and so on. So if we talk about, to begin with, it's a long journey to actually defining the different parts of all the building blocks. But number one of them is really about, to have the right position of the machine. So of course we can see the trend to optimize the sites. We can also see the trend to using movements without any operator when it will become a hash area and hash environment to be sure that we don't hurting anyone. Still the position, of course, it needs to be controlled by the satellite systems, but also in conjunction to have that with the normal, land-based network as well, to be able to get the high accuracy on the position by a centimeter and so on. And then, of course, moving forward with that, it's up to where the machine will be used. I'm lucky enough to have a lot of heritage with the aerospace in the Parker groups. So by utilizing that experience into our mobile components have been a big benefit. And this is about how to implement the functional safety. And when you talk about functional safety, it's about how we do the whole verification of it. And the whole journey. Model-based is a key element by the process. But it's also about how to do hardware in the loop and simulation. So having the heritage of aerospace, this has been there for the last 30 years. What you can see here, it's about this Iron Bird and also the simulation hardware in the loop have been a big benefit for us when we're designing the functionality into the mobile products. So that have given us a lot of, I would say, new impact to speeding up the design process. And how about now what will happen on the mobile machinery itself? And of course, it starts with the control system, what will become a heart of our self-driven machines. So if we start to talk about what will be the work method itself, now we need to define the performance level on the functions, what we will do. And within the performance level, we are used to works with a V model where we're making the software into the hardware and also into the functionality on the machine itself. So here is an example. You're starting to select the component, what have the right, reliability data, the right sea levels, what actually the machine have defined on your assessment on the risk on the machine itself. And then you can see here on the right side, then you're choosing the components, what we have in the Parker ecosystem to be able to get the functionality, what you would like to use. And this is about the process itself. And I think we have pretty much of a discipline when we talk about the V model. I mean, as an engineer, and as you see something going very quickly, you get so excited directly to coming down and start to do the coding. Easily you forget to do the verification to actually make sure it works as you actually have defined it when you did your risk assessment on the performance level. I can also see a risk now when we have shortage on the semiconductor business. You don't find a product what should be there, for example, a sensor, and you find something else. Make sure we take not only to put it into our system, you need to go back, you need to do the risk assessment to that working, and then go back into the verification and the validation of the whole system design. So you don't create something what will actually be dangerous, not only for the operator, but everyone around it. So how do we do in this then? First of all, the control system, it's also need to have a good platform, what you actually can using a lot of these platforms. And functional safety would be a key element that we know that we don't need to evaluate the hardware and the operating system when you're designing your application layer itself. The second piece, when we talked about in the beginning, that is the demand to have a model-based code environment. So you can using in this case we're using the MATLAB Simulink model pretty much to be able to make sure that it actually acts as it should be doing. And otherwise, it's a huge of responsibility for each software engineer if you don't having this kind of model-based code structure into your software itself. And then, of course, simulation of the whole machine, we can using AimSim, for example, to do the whole motions of it, again, to be able to do that. And of course, in the platform, the software, that you need to have both the logic simulation portion of it, as well as the model coming from the machine level. It's important. But not only that, when the machine starts going and moving without any operator, sensor become a very, very important factor. So you get the feedback loop, know what's going on, and so on as well, to be able to see with the movement, so you don't doing anything if that should be self-propelled and self-moving. So you have in this case here, you have pretty much of, I would say, analog sensor piece coming into the controller, but you also have a lot of sensors, what is more smart sensors. So in this case, you have this position module, so you know where you are, but also inclinometers, what we know the motions, you can get the gyro on it, what is the acceleration, deceleration, movement on the arms, become more and more important to be able to see what the decision the vehicle need to take by themselves. So continue to moving forward with that. You also need to have the implement functionality a part of it. And you can see here we started to talk about directional valves. And the same journey is there for directional valves. That is when we have solutions with sensor built into the valve. You have position sensors for the main spool to increase your diagnostic coverage on the movement itself. And as you can see, sensors become more and more important to actually be able to take good decision. Then we continue down. We can see here the next portion I will talk about here, it's about the steering. Now you need to design if that steering need to have a safe stop, that means a redundant stop, or if that should continue to go as a limp home situation. So with one fault, you can still steer it. If that had been in the hush environment, you can come out from that with a limited performance, but you have a fault-tolerant system layout on your movement and your machine directive. So again, it's a lot of inputs, a lot of building blocks to be able to move that forward. So you can see here that is that directional valve on the top. You can see that steering valve, and you can also see that steering by wire valve, what actually have a redundant fault-tolerant solution built into it. I just want to say to have it a fault-tolerant steering valve is much about the sensors itself. We need to make sure that the dual circuits, what do the steering application, will work, especially if you have a primary steering solution. Of course, you can see the movement, but how can we make sure that the secondary steering works when we need to have it? By doing that, we're adding sensors again to make sure that we have pressures and everything is ready to go, so we don't have a fault before we're needing it. So it's important to have the sensor adapted. Also, the temperature sensor, it's important here, so we don't have any temperature shocks to be able to stick or have uncertain movements onto it. If we now leaving the hydraulics and see where will the power coming from, so we can start to talk about electrification. So in this case, you need to have a inverter. Inverter need to be designed for the purpose what is mobile and rugged. But it also need to have safety standards built into the drive. Now when a lot of power coming into the vehicle by electrical, how to make sure we actually have that also safe so we can control it in the best way. Also including now the hydraulic functionality inside the drive when we spin the motor become more and more important to actually know so we don't doing something wrong on the pump side when we should not have been doing that. On the electrical motor side, in this case we have a global vehicle motor where we have a very dynamic and high efficiency motor on the market. And the high dynamic is actually built for be responsive when we talk about what we can do for the hydraulic, controlling pressure by spinning the pump, become more and more a standard work in this market space. And of course you have diagnostic coming out from the motor and the sensors there, and you have multiple pump technologies. So when we talk about the different pump technologies itself, Parker have a variety of different pump technologies. So in this case, we talk about a gear pump, we can talk about a vane pump, and we can talk about the piston pumps. And why this is important, that is every pump technology have a purpose to fulfill in a mobile machinery. So if we start with a gear pump, cost efficient and very robust. So that's really good. Take a vane pump, you have that silence in the nature. But we can also start to talk about quadrant. That means can you doing energy recovery of it or not? That become also very important. And then you have a piston pumps, in this case a bent axis, what you can have 4-quadrant operation. That means you can spin the pump 2 ways, you can also pressurize it in 2 ways. So why would this become important? That is again, if you would like to recover the energy, then of course we need to be able to charge all the kinetic energy out from a boom, for example, coming back into the batteries. Then we need to have the three options on these configured e-pumps. Now when we talk about this functional safety, so here is an example on our new generation of inverters for the mobile circuit. And you can see you have the high voltage power, you have the low voltage for doing the controls, and of course you have the CAN interface to doing the commands back and forth. But you also have a secondary, communication coming in for the safe torque off. So even if you have issues on the first line of channels coming in, you also have a secondary channel to actually turn off the torque, to spinning the motor when it's needed. And really what this is all about, this is now to go into the summary of it. So if we take now how a system layout can look like, you have the drive, you have the configured e-pump, you have the next generation of valve integration with all the sensors to increase your diagnostic coverage, and also all the feedback sensors, what you can get back from the movement, either on the traction or you get it back from the motion or the implement functionality. In the end, the functionality is really designed in a control system, what gives you the capability to using the position, very accurate, but also feeding up the data into the cloud to do other type of services, what is needed, how the condition is on the machine. So summarizing everything of that, by having smart and safe components, to focus on functional safety by having a fault-tolerant system layout, they give us the journey really to be on the part of autonomous machines for the future. So by that, I will actually stop talking and go over a little bit if you have any questions, so please let me know so we can answer that if I'm able to. Okay, very good crowd here. I need to drag it out from you then, huh? You've been listening very politely, I get that. And everything makes sense then? Okay, very good. Anyway, thank you very much. My name is Nils Henriksson. If you have other questions, if you don't want to talk about it here, welcome up here or send me an email. I will be happy to answer your questions then. Thank you very much.